Hello students, welcome to week 5 live problem solving session for analog electronic circuits course. I'm audible clearly, right?
Yes, ma'am, you're audible.
So today we will be solving problems based on same BJT and MOSFETs, but we'll see different configurations today. So moving on to this first problem. So in this problem, it is given that it's a circuit with what type of BJT configuration?
PNP.
Yeah, BJT is NPN. Is it NPN or PNP?
Ma'am, it's a PNP.
What type of transistor it is? It's a PNP,
PNP.
right?
Yes.
And how the transistor has been connected is the point, right? So what terminal is this?
Ma'am, this is the source.
It's a BJT.
Oh, sorry.
So
Ma'am,
what?
it's emitter. It's a
Emitter, yes. It's emitter. What about this one? This is base, right? And the
yes,
remaining
ma'am.
one is collector. So
Yes,
now
ma'am.
looking at the configuration, what type of connection is this? What type of configuration is this?
Common collector.
Common collector. How do we know it's common collector?
Because collector is common in between both.
Yeah, we are giving input to the base and taking output from emitter, and collector is common between the two terminals. Hence, this is a CC amplifier. So when we talk about a CC amplifier, so what are the properties that comes to your mind when we talk about a CC amplifier? Properties of CC amplifier?
Ma'am, it has a low gain as compared to common emitter.
Okay, CC has low gain. Which gain?
Voltage gain.
Okay, it's V out by V in. Okay. What else?
Ma'am, input resistance is also different.
Okay. Input resistance is different. What else?
Output resistance is also different.
Input output resistance will be definitely different. Yes. From CE configuration, right?
See, yes, ma'am.
What else? What else have you heard in considering CC amplifiers? Have you heard anything?
Sorry, ma'am, I don't remember.
Have you heard of a buffer?
Yes, ma'am. Yes,
Buffer, what does buffer mean?
ma'am, it is. Um, mm, Sorry, ma'am, I am unable to describe.
Yeah, so basically, what does a buffer mean? Buffer means your input is translated to output. Okay. So, but you'll ask, like, why do we need a buffer, right? When input is being translated to output, why do we need a buffer circuit?
It's
I,
efficient.
I can simply connect a wire, right? In a wire, your input will be equal to output. If it is a very small wire, the input will be equal to output. So, but we are using a buffer. It's a proper circuit. So, what is the use of this buffer? Can you think of something that comes to your mind? When I say it's a circuit which will give you a output voltage equal to input voltage. But why do we need that circuit? Can you think of anything?
First of all, ma'am, it is efficient.
In what terms it is efficient?
Ma'am, it has low input impedance and how high output impedance.
Okay. Low input impedance and high output impedance. What majorly will a buffer do? Okay, efficiency you are saying in terms of resistances. But what else can we get from a buffer? Acha, you have talked about voltage gain, right? What about current gain? What do you think?
Ma'am, current gain will also be low.
Current gain will be low. In this above figure, this is a buffer circuit, okay? CC
Sorry, ma'am,
amplifier.
current gain will be high.
Yes,
Okay.
current gain will be high. So in a buffer circuit, voltage gain is low, current gain is high. And what is the usage other than this? So what else can a buffer circuit provide? How about if we think of in terms of frequency and delays? Can you think of anything?
Ma'am, it is used for impedance matching.
It can be used for impedance matching. Yes. So how can we use it for impedance matching? So if I want to make a voltage amplifier, how should my impedances be? Let's say Zin. What will be the value of my Zin for a voltage amplifier? Yes, Zin should be
Low.
low and Z out should be
High.
high. But let's say if we are connecting an amplifier, let's say if I talk in terms of a MOSFET, so here we give an input, source, drain. From here we take, okay, wait. Should my output impedance be high? First of all, voltage amplifier मतलब क्या होता है? Voltage amplifier means voltage to voltage conversion, right?
Yes, ma'am.
So if I want my output voltage to completely drop across my load, so let's say this is R0, which is the output impedance, or Z out, let's say Z out versus RL. I want my V out to drop across RL. So so what will be the value for RL? Let's say here it is the amplifier. Yes, there is an amplifier and this Z out is like this, and there is this RL, right? So in this type of configuration, see why I have put my Z out in series?
Ma'am, the voltage will be divided.
Yes, and when we talk about a voltage, and voltage is always represented in Thevenin equivalent form, right?
Yes, ma'am.
So it's basically plus minus V in series Z. Whereas when we talk about Norton equivalent, it's for current, where it is like current in parallel with its resistance. Z in or Z out. So this is how it is represented, right? So now when we are saying it's a voltage to voltage conversion for voltage amplifier, then I want my voltage, that is V out, to completely drop across my load, right?
Yes, ma'am.
So for this, what should be the value of Z out?
Z out should be low
Z out should actually be low.
and RL should be high.
RL should be high, as high as possible, so that all the voltage output that we want, it should not drop across the transistors or the amplifier's output resistance or impedance. It should drop across the load. That is what we want, so that there is no wastage, right? But so what is this configuration? If I connect it like this, What is this configuration called?
common source.
Common source. So here we know that this impedance is very high, right? Zn is very high. है ना?
Yes, ma'am.
And what about V out? What about RD?
RD should be low.
So do you know like the relation between RG, RD and RS? How they are related to each other? Or at least what is the trend they follow? Like which one is largest, which is smallest?
No.
No? Okay, let me tell you. So in case of a MOSFET, RG is much larger than RD, then RS. Okay, so this is the trend it follows, which makes RD actually larger. So its value is 1 by GD, like close to 1 by GD, RD, whereas RS is close to 1 by GM. Okay, and GM and GD are 3 orders apart, at least 3 orders apart. So there is a difference of 1000 times between RD and RS. Do you understand that?
Yes, ma'am.
है ना? So RG is technically infinite, but practically it's in hundreds of mega ohms. Okay, RG. So it's much higher. RD is in terms of 1 by GD, and GD is mostly in microsiemens. So which makes it in mega ohms, the resistance in mega ohms, right? And GM is in millisiemens. So which makes the source resistance in kilo ohms. Okay? So because of this trend, it makes the drain resistance higher. Okay? But for our voltage amplifier to like work or behave properly, we need low Z out, right? So after this, what we do, we actually use a buffer circuit and we take the output from here. So this output actually, it will maintain the magnitude, but it will match the load according to, like it will reduce the, or will use this buffer for impedance matching. And our load will actually be connected over here. Is this clear?
Yes, ma'am.
So this is the basic usage of a buffer circuit. In terms of BJT, the buffer circuit is CC amplifier or CC configuration. We call it as emitter follower also. Why we call it as an emitter follower? It's because IC is almost equal to IE, and the voltages are like input terminal and output terminal voltages are almost equal. Okay, so that is why we call it as a buffer circuit. And when we talk about MOSFETs, in MOSFETs the buffer circuits are CD configuration. Okay, so in BJT buffers are CC configuration. Yeah, so buffer circuits for BJT, it's CC configuration. For MOS, it's CD configuration. Okay, so we'll work on both these configurations today. So here the first problem was based on BJT based buffer circuit. Okay, is the discussion clear? अभी तक जो पूछा कुछ doubt है?
Yes, ma'am, it's clear.
Clear, right? Okay, so now let's proceed with the first problem. Yeah. Okay, so this was the circuit given, and what is the problem? We have different values with us. So VB, VEB, by 10 pico, C mu 5 pico. Put it 26 milli. VBB 4, VCC 10. VBB 4 volts, 10 volts. RS 100K. RE 10K. RC 2K. And CL is 100 picofarad. Okay, all these values have been given to us. Now what we have to find out is, by considering the DC current analysis, find the maximum output swing signal without sufficient distortion for an input sinusoid signal for the amplifier circuit shown. And okay, and today we'll be talking or we'll be working on all the numerical answer type problems. Okay, so we won't be seeing any options. And in exam you'll also find these numerical answer type problems, so it's very important for us to go through these type of problems and be very sure with our answers whether we are getting the correct answers or not. Okay, so yeah, we have to find maximum output signal swing. That is the idea, using all these values which are given. So to find the output swing, what is it that we need? Last time we discussed, right, output swing. What is the output swing? Yes, what is an output swing?
VE minus VEC saturation.
Sorry?
The minimum value between of VE and VEC saturation. Oh, sorry, VE and minus VEC saturation.
Okay, that is what you are saying mathematically. But what is actually the sense behind output swing? What is output swing? Or why we discuss output swing?
So we can get the idea of the sinusoid which we can get without distortion.
Yeah, which we can get without distortion. Or for linear amplification, what is the output that we can get? Maximum output swing that we can get, right? So yeah, if the so what is the range we can vary it between VCC and ground, right? This can be the maximum range. But here, depending on the bias point where we are getting, we'll find the swing. That is the idea. So what are the points that we'll need to find out to find the swing? What are the bias points or voltage levels which we need to find out the actual value of swing? How will we find the swing? We did this last time also, right? How did we find the swing? What was the first step?
When we will find VCE, VEC.
So first of all, when we have to find the output swing, we need to know the bias point or V out, right? V out's value. We need to figure out where the V out can be placed. You know?
This one.
And depending on this V out and other conditions, we'll find out what is the actual swing that we can get. So first of all, let's find out V out. V out, how will we find V out? So which is VE over here, right? So how do we find VE or V out? We can find it as VCC minus IERE. Here IE is almost equal to IC. So yeah, so we can write it as V out equal to VCC minus ICRC or ICRE as our V naught, right? This is one expression. And secondly, how can we write, like, we have to find this V naught. We know VEB, this value. We know this. So how about if we write this KVL using this value, can we find V naught? We can find it, right?
Yes, ma'am.
So how will we write it? It's like VCC minus VBB. The potential difference is equal to ICRE plus VEB plus IBRS, right? This is how we'll write.
Yes, ma'am.
इसको we can consider IC or IB depending on your wish. So if we take it as IC, so it will be IB times 1 plus beta RE plus VB plus IBRS. If we take it as IC, then it will simply become IB into beta into RE plus VB plus IBRS. Right, both ways we proceed. And also one thing that I want to mention is when there is a numerical answer type problem, there you will get a range. Okay, so you can give your answer in a certain range. For example, your answer can vary from, let's say if the answer is between 7 and 8, so your answer can vary from 7 to 8 and you'll get the marks. So why that variation is allowed? That is because people take several assumptions, and depending on which your minute values will change. So if let's say if we consider this assumption of IC almost equal to IE, the results might change by very minute amount. So those things can be considered. Okay, so you need not to worry कि every time क्या होगा. इतना मतलब if the answer is, let's say for numerical answer type, if the answer is 7.25, even 7.3, 7.4, 7.5 is sometimes acceptable in numerical answer type. Is this clear?
Yes.
And why this changes come? It is basically depending on your assumption. Somebody, let's say for thermal temperature, somebody has taken 26 millivolts and it was not mentioned in the question. So somebody has taken 26 millimole, somebody has taken 25 millivolts. Difference will come there. Or if somebody takes IC almost equal to IE, the difference will be there. So that's why in numerical answer type, a range of values are acceptable as answer. Okay. So this is also something I wanted to mention. So we can proceed either ways. है ना? So this is also correct. This is also not wrong. This can also be used. Depending on if it reduces your calculation time and everything, you can go ahead with this assumption. It is completely fine. So for now, let's go with the actual one and why to take the assumption. And you can check with by taking the assumption if there is like what is the magnitude change that you get. Okay. So yeah, this is what is known. VC minus VB is how much? It's 6. 10 minus 4 is IB 1 plus beta RE, that is 100 into 10K plus 0.6 volts plus IB into RS. RS is 100K. Yeah. So from here we'll get the value of IB. What is the value of IB that we are getting?
Ma'am, actually, ma'am, there will be a bracket after beta.
There will be a bracket. Hey, yeah. Yes. 1 plus beta into Re. Yes. Because it is IE, right? So IC plus IB. So from this expression, we can find IB. So what is the value of IB? And the moment we find IB, we can find V0, as well as we can find this VC also. You know? VC will be simply ICRC. So what is the value of IB that we are getting?
It's coming around 4.86 microamperes.
4.86 micro.
Like, uh,
Can you check the values once? Also your units. So IB should come around 0.5 milliamperes. Can you check your calculation once?
is from 0.5.
You're getting 0.5, right? Yeah. So it's 0.5 milliamperes. So the moment IB is 0.5 milliamperes, what will be the value of V0? It's 10 minus, let's say 101 into 0.5 is into RE. How much was RE? 10K. Also VC is IC into RC. RC is 2 kilo ohms. Yeah, so what is the value of V0 that we are getting and what is the value of VC that we are getting?
V0 is minus 495.
V0 is? How much is V0 that we are getting? Minus 495.
Yes,
What about VC?
VC is 100.
VC is 100.
Yes, ma'am.
Is there something wrong with the units? It's actually 100. But is 100 volts possible? No, right? Because maximum VCC is 10 volts. So that means there is something wrong with our calculations. Wait. IB, how much was the IB that you were getting? It was 486, right? 4.865 microamps. This is actually correct. This is IB only, which is like IB is close to 5 microamperes and it is actually IC, which is 0.5 milliamperes. Makes sense. IB is 5 microamperes, IC is 0.5 milliamperes, which makes your V out as 10 minus I into RC, sorry, I into RE, which is 10 minus, if I say it to be 0.5 milliamps only, 0.5 into 10k, and VC will be IC RC, so it is 0.5 milliamps into 2 kilo ohms. Yes. Yeah. IB micro में ही रहेगा.
V out is 4.95.
V out is 4.95. Okay, V out is 4.95, and VC is 1 volts, right?
Is 1 volt.
Yeah. So see, here we made the mistake, but where we got it, like, yeah, we have done the mistake because VC values were going beyond the range. So we need to keep that also in mind, because here we don't get options, right? So we need to debug our answers ourselves. So the moment we saw the values were going out of range and we were getting negative voltage values, which is not possible, that means we have done certain mistakes somewhere. So here IB was actually 5 microamperes. It was IC which was 0.5 milliamperes. But the moment we changed them, the values were going out of range. So that's how we got to know that we have done something wrong. So yeah, here now see, here we have VCC, which is 10 volts, ground, which is 0 volts, right? And this VC is somewhere here at 1 volts, you know, and your V0 is almost close to 5 volts. So let's take it as 5 volts. Okay. So if you look at it very carefully, your V0 has no boundation for upper limit. Like it can go from 5 to 10. There is no boundation here, right? But when we are coming down, we know that VEC SAT is there, which was 0.3 volts, right? VC SAT was how much? 0.3 volts. So now the moment your V0 is coming close to this VC, it should maintain at least a gap of 0.3. which brings in this demarcation of 1.3 volts, right? Is this clear? ये 1.3 कहाँ से आया?
Yes, sir.
है ना? So now how much we can have as swing? So double of either this or double of either this, है ना? Now which one to select?
Minimum.
Minimum of the two. So your output swing is actually 2 times minimum of 10 minus 5 or 5 minus 1.3. So definitely it is 5 minus 1.3, right? So which is 2 into 3.7. So that is 7.4 volts peak to peak. This is the output swing that we are getting. Is this clear?
Yes, ma'am.
Okay, so this is how we have found output swing last time also. So here also we are doing the same thing. Now moving to the next problem. So here it says, by considering the instantaneous current analysis, find the maximum output signal swing without the distortion. Okay, so earlier what was the question? Considering the DC current analysis, find the maximum output signal swing. Here the question is, considering the instantaneous current analysis, find maximum output swing. So what is it that comes to your mind when we say we have to do an instantaneous current analysis or DC current analysis? What is it that comes to mind? Like, does it give you any hint, or are you able to understand what might be possible, like what they are actually talking about? Can you think of anything? The moment you see these words like DC analysis or instantaneous analysis, yes. See, right now what we did was DC analysis, है ना? According to the question, we got the answer also, and the answer is correct. I'm telling you. Now we have to do instantaneous current analysis. So what is it that will be different in this case? Yes? Anything that comes to mind, what might be different? Anything? Anyone? No? Jyoti, what about you? Sanjiban?
Yes, ma'am.
What
Yes,
is
ma'am.
it that might be different from DC current analysis to instantaneous current analysis? See, here also we have to find output swing. Earlier also we had find output swing. So first question is, are these two same? Earlier what we did, earlier also in previous question, here also we found the output swing, right? And now also it has asked us to, like, the question has asked us to find output swing. So my first question is, are these two answers going to be same in question number 1 and 2? So will you be asked two questions with same answers simultaneously?
Actually, I think we have to find the swing for the current output current.
Yeah, so here, okay, so let me tell you, these two are two different things, okay? DC current analysis and instantaneous current analysis, both are very different. Okay? DC, so now where the difference actually comes, let me explain you that. So try to understand it very carefully, okay? And it's not very difficult, it's more like analyzing the circuit, okay? So let's see. If in this circuit your VE or V0 is actually VCC minus IERE, right? Let's consider IEA is almost equal to IC. Okay, there is no much difference, right? So it's almost equal. And your VC is actually IC RC, right? This is okay, right, for everyone?
Yes, ma'am.
Now, let's say somehow your IE increases. You have done biasing or you have changed something, your IE increases. So what will happen? Because of this, definitely your IC would also increase.
IC for IC increases, the output will be increases.
No, output will not increase actually. See, the moment IE will increase, IC will also increase. And the moment IC increases, your VC will increase.
Okay.
Right? What about V0? The moment IE increases, VC minus IERE will actually reduce. So it will actually reduce your V0. Is this clear?
Yes, ma'am.
So there is an inverse relation between your V0 or VE with VC. Is this clear? So When V0 increases, your VC reduces, and vice versa. When VC reduces, your V0 reduces, your VC will increase. Is this clear?
Yes, ma'am.
So till now, what we considered our VC to be constant at 1 volt. And that's how we derived 1.3. And we said this difference will give us the output swing. Right? But actually, that is not true. Here your VC is not fixed. It is also going to change. Because VC and VE are actually interdependent, or V0 and VC are actually interdependent, and they are inversely proportional to each other. Right? So now here we will not get the same swing. The swing value will definitely change. Right? And where we will see the effect? Will we see the effect in upper half of the swing? Because of change in VC? No, right? Because VC is here at 1 volt for DC analysis. So it will fluctuate between 1 to 1 above something and 1 below something. Hai na? So the effect will again come in this part only. Right? So now what we need to understand is actually how much is the change that we are going to see in VC, and because of which how much is our swing that is going to change. That is the idea. Is this clear?
Yes, ma'am.
Could you understand the discussion, like what has actually changed from DC analysis to instantaneous analysis?
Yes, ma'am.
Okay. So we know that VEC SAT is 0.3 volts, right? So if we write VEC, how can we write it? It is VE minus VC or V0 minus VC, right? V0, how we will write? V0 is VCC minus IERE, and how we are writing VC? It's actually ICRC, right? This is how we are writing it. है ना?
Yes, ma'am.
So considering that IA is almost equal to IC, we can write VCC as VCC minus ICRE minus ICRC to be 0.3. So from here, if I have to calculate how much is the value of my IC that I am getting. How much is the value of IC that I am getting from this?
Ma'am, around 80 milliamperes.
80 milliamperes.
Yes, ma'am.
Did you check the units again? It's 0.808 milliamperes. So it must be 80 microamperes.
Sorry, ma'am. This one.
Yeah. So it's this is the value of IC and it is also the value of IE. So the minimum VE or V0 that we can get is VCC minus IC RE or IERE, which is 10 minus 0.808 into 10k. So how much is this VE that we are getting? How much is the value of VE that we are getting?
Ma'am, 1.9.
1.9. 1.9 to be very accurate. So this is the VE that we are getting. Now what is this VE that we have got right now? This is the VE that your circuit can arrive at the edge of saturation or at the edge of that saturation and active region, right? Why I am saying this? Because I am calculating for the condition at VEC sat, right? So at that VEC sat condition, what is my current that I can get? And from there, what is my VEC that I can get? That is what we have calculated, right?
Yes, ma'am.
Now, earlier the VEC was for DC point, it was at 5 volts. Now, we have found out that at this edge of active region or at edge of saturation, your VE can at max go to 1.92 volts, right? But here also there needs to be a VEC sat which needs to be maintained, right? So if I say my VC was at 1 volts and here it is 1.92, this is VC, this is VE. So if I zoom in at this point, so it's like 1.92 volts ka VE, one volt ka VC, okay, and here we have ground. But so this is the minimum value your VE can attain. तो इससे 0.3 नीचे तक ही your VC can go, right? So your VC can go till 1.62. Is this clear? ये 0.3 तो it will maintain, right? To keep your transistor in active region. Is this clear what I am trying to say?
Ma'am, can you please repeat this point?
Sorry.
Ma'am, can you please repeat this point?
So see, this VE that we have found out, do you understand what is this VE? ये VE जो हमने नया VE फाइंड आउट किया 1.92 वोल्ट्स, ये क्या है? ये समझ में आता है?
Yes, ma'am.
What is this?
Minimum voltage.
Yes, minimum voltage, so that your transistor remains in active region, right?
Yes, ma'am.
So if your transistor is still in active region, that means it will also follow that VEC sat condition again, right?
Yes, ma'am.
And we have also seen that now VC is not a DC value, but it is also actually fluctuating, changing with like VE, and they are reciprocal to each other, right?
Yes, ma'am.
So if there is a sinusoidal trend in VE, there is also a sinusoidal trend in VC, right?
Yes, ma'am.
So VC भी एक साइनोसॉइड फॉलो करेगा और VE भी आपका एक साइनोसॉइड फॉलो करेगा, and your VC will also follow, so VEC will also follow that VEC sat का condition of 0.3 volts, which means अगर आपका और
VCE
C
shouldn't it be plus 192 1.92 plus 0.3?
नहीं see, VE is higher, is at higher potential, VC is at lower potential. Your VC can never cross VE, right?
Yes, ma'am.
अगर यहाँ से 10 वोल्ट आपका ड्रॉप हो रहा है तो देर विल बी अ ड्रॉप अक्रॉस दिस RE, देर विल बी ड्रॉप अक्रॉस दिस VE. VE का ड्रॉप मतलब क्या होता है? VE का ड्रॉप मतलब इस पॉइंट से ग्राउंड तक का पोटेंशियल, राइट?
Yes, ma'am.
VC मतलब VC दिस पॉइंट टू ग्राउंड तक का कंप्लीट पोटेंशियल. दैट इज व्हाट इट मीन्स,
Yes, ma'am.
है ना? So if I say as you are saying, like VC will go beyond 1.8, that means this potential has gone beyond this potential. Is it even possible? तब तो नेगेटिव रेजिस्टेंस वाला कॉन्फ़िगरेशन आ जाएगा ना?
Yes, ma'am.
Yeah, so that is not possible. So that's what I am saying. So is this clear, Arjun?
Yes, ma'am. Yes, ma'am. It's clear.
Yeah. So now, okay, yeah. So what I am saying is, we know that VE is inversely proportional to VC. We have seen earlier, and qualitatively, है ना?
Yes, ma'am.
So that means when VE is at minimum of 1.92 volts, your VC will be at its maximum, right?
Yes, ma'am.
But we need to find out, okay, what is that maximum value that VC can attain? So for that, it has to also follow this VC sat condition, which is of 0.3 volts. That means the distance between your VE and VC, that is VE minus VC, should always be greater than 0.3 volts, right?
Yes, ma'am.
So when if there is this sinusoid, let's say, so the moment your VE has attained this value, your VC will actually boost from 1 volts to this point. और वो कितना boost होगा? It will actually boost till 1.92 minus 0.3. Did something go wrong? Are you able to see my screen?
Yes, ma'am. Yes, ma'am.
Okay, because all of a sudden my screen sharing has stopped. Wait, let me reshare again. Okay, is this visible? Yes, it is visible, right? My screen, iPad
Yes,
screen.
ma'am. It's visible.
Yeah. So yes, so that is what I am saying. Look at this big picture. Here your VE is fluctuating. This one is VE. Okay. And this small sinusoid is actually VC, that it can fluctuate. Okay. So now what I am saying is, this VC, it can attain a maximum value, VC max can be 1.92 minus 0.3. Is this clear? So which is actually 1.62 volts. Is this clear?
Yes, ma'am.
So this VC max का concept is clear? So instantaneous में क्या हो रहा है? Your VC, earlier we considered VC to be fixed at 1 volt, but यहाँ पे we are also seeing the variation of VC with VE, है ना? This is what we are trying to do. But when it is asked कि you have to find the output swing, तो output swing का क्या मतलब है? हमको इस बड़े वाले साइनोसॉइड का ही swing देखना है. Because this is output, right? Your VE is the output, right?
Yes, ma'am.
So ये जो अभी डिस्कशन किया, इसमें ultimately we have to find the swing in VE. So वो कितना होगा? It is minimum of twice the minimum of 10 minus 5 or 5 minus 1.92. So swing will actually be how much? It is 6.16 volt peak to peak. Is this clear?
Yes, ma'am.
So earlier we were saying no that our output will actually go till 1.3 volts. That is actually incorrect. Your output can swing only till 1.92 volts. It cannot go beyond. That is the idea. Clear? Any doubts? Was it too much information? You could not follow?
No, ma'am, it was fine.
It was fine, right?
Yes,
What
ma'am.
about others? Swati, Sanjiban? Sorry, Jyoti, Sanjiban? Sorry. Jyoti, Sanjiban, are you there?
Actually, I'm a little distracted, so I just didn't hear few things. But I'll just catch up with our session in send on the YouTube.
Oh, okay. So maybe yeah, you can catch up. So yeah, here we were discussing about DC swing and instantaneous current analysis and swing base coming
I
out.
heard a few things.
Yeah. Okay. So maybe you can catch up, and just in case if you have any doubt, you can revert back. Okay.
Yeah.
So Arjun, you are following continuously, right? So is it clear? Could you understand?
Yes, ma'am. Everything's clear.
Everything is clear, no? Okay. Just in case if you have any doubt, please feel free to ask. So now the next question is find the input resistance looking into the base of transistor without considering the RS. So in this particular circuit, we have to find the input resistance without considering this RS. So what will be the resistance? Yeah. So shall we make the small signal model for this and then solve the resistance? It will be easier, right? So let's do that. Let's make the small signal model for this transistor. Base, this is emitter, collector, there will be RE, RC, R0, this is C. So did we miss out something? Base R pi GMVB R0 RC and RA. Yes. So this is how your small signal model will look like, right? This is how it will look like.
Yes, ma'am.
So इसमें you have to find Zn looking from this base terminal. What is the total resistance that we will see? Okay. So let's begin. Maybe we can solve these 2 points and we can come up with the final answer. So Zn or Rn or Zn will be, how will we write Zn? It's VB by IB, right? Zn is VB by IB or we can write it as VB by IB, and VB by IB ko we can write it as VBE by R pi, right? We can write it as VBE by R pi, right? And to mind you, this is our V naught. VE is our V naught, hai na? So when I say VB, it actually means VB minus V naught by R pi. So which is actually R pi by 1 minus V naught upon VB. Is this clear? Zn का एक्सप्रेशन ये जो आया ये क्लियर है?
Yes, ma'am.
So now here we have to actually find what is this V0 by VB. And this is actually the task that we have to perform. R pi हमको पता है. How do we write R pi? What is the value of R pi? जो इंटरनल बेस रेजिस्टेंस होता है, हाउ डू वी राइट इट? दिस आर पाई. व्हाट इज द एक्सप्रेशन फॉर दिस आर पाई? यस
Ma'am, beta upon GM.
Beta upon GM, right? So this we know. Beta we know. GM, did we find out GM somewhere previously? But what about GM? What is the expression for GM? We know GM, right? IC by VT. So this is also we know. So we know GM, we know beta, so we can find R pi. What is it that we don't know? We don't know V0 by VB. है ना? So for this actually we are going to solve few equations to find this value of V0 by VB, and the moment we substitute it we'll get the Zn. Clear? तो V0 कहाँ पे है? C. V0 you will find at this particular terminal. VE is this, VB is this particular terminal. So you have to solve KCLs to find this V0 by VB. So let's do one thing. Let's first apply KCL at V0 and see what we get. Okay? So what will, yes.
Ma'am, can't we write directly that Zn is equals to R pi plus Re multiplied by 1 plus beta?
Can we write it as R pi multiplied by R pi plus Re into 1 plus beta? Okay. So, but why we can't write is, see, earlier we had ground nodes, right? C was grounded. Now here C is not grounded, so this will come in parallel. This RC wala term will also come in parallel. And this is actually not, so from the small signal model it appears to be very easy. ऐसा लग रहा है ना कि यहाँ से like this IB will flow, and from here we'll say the IE will flow, and simply we'll write it in terms of IB and we'll get the Zn. But actually that it is not that simple, because the presence of this RC is also there. This RC is there, the RE is there, and your V out is at this point. This is the problem. Your V out is also at this point. So because of all these, now actually when we are solving, you will realize that this term that comes out, no, it's a very complex term, and we'll see how it comes out. Okay, then maybe it will give you a clear picture.
Okay.
Is it okay?
Okay. Yes, ma'am.
Yeah, so maybe we'll calculate and then we'll see, okay, can we write it as that, or can we simplify it to that form of Zn to be R pi plus 1 plus beta of Re, right? So let's check while finding. We'll get a very complex term, but can we reduce it to this form? Is it even possible or not? That's what we'll check. Okay. So yeah, meanwhile, let's quickly write down the KCLs at different nodes and try to find this term out. So when I'm writing KCL at V naught, it will be V naught by Re plus GMVEB plus V naught by R naught V naught minus VC, yes, V naught minus VC by R naught. Anything else और कोई term रह गया? Plus V naught minus VB by R pi. So how many current branches? 1, 2, 3, 4. Right? Are we left with something? No, right? VEB को भी I'll change it. VEB को we can write it as V naught minus VB, right? So all the things are in similar terms. So it's V naught by Re, GM V naught minus VB, V naught minus VC by R naught, and V naught minus VB by R pi. This is correct? This is KCL at V naught. So let's write KCL at VC. So when we are writing KCL at VC, we'll get, so at this point, it is VC minus V naught by R naught plus VC upon RC plus GM VP minus V naught, because it is actually opposite. So if I write it, इसका direction opposite है ना, तो minus GM V naught minus VB ऐसे लिखते हैं. So there is no confusion. So how many branches we have? 3. VC by RC, VC minus V naught by R naught, and minus GM V naught minus VB equal to 0. ये minus क्यों आया समझ में आया ना? Because it's a incoming current, whereas others are outgoing current. So that's why the convention has changed. Is this clear? इसमें कोई doubts नहीं है ना?
Yes, ma'am. Please.
So now by solving these two, we can actually substitute the value. So we have variables as V naught, VC and VB. We have 3 variables. We want everything in terms of V naught and VB so that we can find V naught by VB, right? So for that we have to eliminate VC. So what we'll do from these two, we'll substitute the value of VC from one to another. So which expression should we substitute? Maybe here we have only one VC, so let's substitute from there to here. But you have to bear with me because it's very complicated. It's going to look very complicated, as you can see here. So like, let's say first, second. So find VC from first, it will be V naught by RE plus GM V naught minus VB plus V naught by R naught, V naught minus Vp by R pi into R naught is Vc. This is what is Vc. We have to substitute this Vc here and here, and then we'll get an expression which is completely based on V naught and Vb. We'll simply separate the two variables and we'll get the solution. Okay? So that is what we are going to do. So will you do the maths or do you want me to do it? Should I give you the final expression? What's your take on this? Or do you want me to solve? So here it is actually Vc by R naught minus V naught by R naught plus Vc by Rc minus Gm V naught minus Vb is 0. So the moment it is Vc by R naught, it will be V naught by Re plus Gm V naught minus Vb plus V naught by R naught plus V naught minus Vb by R pi minus V naught by R naught plus V naught by Re Gm V naught minus Vb V naught by R naught plus V naught minus Vb upon R pi bracket R naught by Rc minus Gm V naught minus Vb is 0. So here let's separate the terms. Okay, V naught one side and Vb, let's move all the Vb terms to the other side. So V naught by Re plus Gm V naught by R naught, V naught by R pi minus V naught by R naught plus V naught by Rc, V naught by Re, let's say V naught by Re plus Gm V naught plus V naught by R naught plus V naught by R pi into R naught by Rc equal to Gm Vb plus Vb by R pi plus Gm Vb plus Vb by R pi into R naught by Rc. So V naught 1 by Re plus Gm plus 1 by R pi plus R naught by Rc Re plus Gm R naught by Rc plus 1 by Rc plus 1 by plus R naught by R pi Rc equal to Vp Gm plus 1 by R pi plus R naught by Rc plus Gm R naught by Rc plus R naught by R pi Rc. So what we wanted to find, it was actually V naught by Vb. So from here V naught by Vb is actually Gm plus 1 by R pi plus Gm R naught by Rc plus R naught by R pi Rc whole divided by 1 by Re plus Gm 1 by R pi plus R naught by Rc Re plus Gm R naught by Rc plus 1 by Rc plus R naught by R pi Rc. Okay, so let's check. Should we further simplify this? Rc R pi So if we further simplify it and write it down, we'll actually get it as beta plus 1 R naught plus Rc by beta plus 1 R naught Rc R pi plus R pi by Re into Rc plus R naught. So when we further simplify all of these and put the values, we'll get something like this. Okay, so we have to simplify it further to actually get it in this form, which is beta's form. And finally, when we substitute all these values, we'll get V0 V by VB to be 0.994. And coming back to Arjun, your question. So here you can clearly see when we are saying V0 by VB, we are seeing the effect of Rc, Re, R0, R pi, everything. So we cannot simply write it as R pi 1 plus beta Re. Is this clear?
Yes, ma'am.
We could write it like that because we didn't have R0 at that time, we didn't had Rc at that time. So we could simply write it as R pi and Re in terms of R pi and Re. But now we have R pi, Re, R0 and Rc. And also, so when these all terms are present, the influence of Gm will also come into picture, and hence the complete expression turns out like this complex expression. Okay. So yeah, finally we have got this V0 by VB. So Zn was how much? It was R pi 1 plus V0 by VB, 1 minus V0 by VB, right? Yeah, so it was 1 minus V0 by VB. So that is actually R pi. Did we calculate R pi? No, we didn't, right? Yeah, expression लिख के सिर्फ छोड़ दिया था. So ये कितना आएगा? R pi will turn out to be, maybe we know the expressions, we can simply write from there. R pi is actually 5.2 kilo ohms. Yeah, R pi is 5.2 kilo ohms. R0, we know it is VA by IC. It's also 120 kilo ohms. So we know R pi, R0, beta, everything, Rc, Re. So from there we can get this V0 by VB to be 0.994, and Zn is 5.2 kilo ohms by 1 minus 0.994. So it is actually The value turns out to be 924 kiloohms. So Zn is 924 kiloohms. Is this clear? It's a tedious process, very lengthy calculation, but yeah, the final answer is 924 kiloohms. Okay? So now once we have found this out, what the next answer is, the next problem is we have to find V0 by V in, that is gain. So how do we find gain? That is V0 by V in.
GM times VBE.
So if we look at the circuit, from here, if I say V0 by V in, that means it's more like V0 by VB into VB by Vin, right? V0 by Vin can be written as this: V0 by Vin into like VB by Vin into V0 by VB, right?
Yes, ma'am.
So this V0 by VB we found out just now. It was 0.994, है ना? What about VB by Vin? So it's like Vin, it has RS, it has Zn, and here it is VB. So if I say VB by Vn, how can I write? I can write it as Zn upon Zn plus Rs, right?
Yes, ma'am.
है ना? So the same thing will come here. So it is Zn upon Zn plus Rs. Zn is 924 kiloohms. 924 kiloohms, and it was 100 kiloohms. So 100k plus 924k into 0.994. So this will become 924 upon 1024 into 0.994. So your gain AV, that is V0 by Vn, is actually 0.9. So which is less than 1, which also shows that the configuration is CC, because gain is less than 1, right?
Yes, ma'am.
Okay, so coming to this next problem. This problem is based on MOSFET. So here R1 is 5 kilo, R2 is also 5k, C1, C2 are 10 microfarad, load is 100 pico, VDD 10 volts, RL is 2 kilo. These are circuit parameters. Next are MOSFET intrinsic parameters. Oh, sorry. So yeah, just 10 volts. It is given that lambda is 0.01 volt inverse, CGS is 10 picofarad, CGT is 2 picofarad, VTH is 1 volts, kW by L is 2 milliamps per volt square. Anything else? Done. So we have to find GM. of the transistor. So what is the GM of the transistor or GM of MOSFET? For saturation, it's VGS minus VTH, right? This is for saturation, है ना? So first of all, we need to check whether our transistor is in saturation or not. So what type of MOSFET is this? NMOS, right? So this is
Yes, ma'am.
drain, here it is source, this is gate. What is the gate potential? VG? It will be 5 volts, as both the resistors are 5 kilo ohms, है ना? So VG is 5 volts. ID, let's say, assume the transistor to be in saturation. Assume saturation. So the current expression will be kW by 2L VGS minus VTH whole square, right? So ID is kW by 2L will be 2 by 2 milliamps per whole square. VG is 5 minus VS minus VTH is 1 ka whole square. Now if we look very carefully, VS is actually ID into RL, because this is series, so same current will flow, right? If ID is flowing through the transistor, that same current will flow through the load. And since this is a DC current, capacitor will block, so there will be no passage of current through the capacitor. So VS is actually ID into RL, which makes our expression of ID as ID into 1 milliamps per whole square into 4 minus ID RL whole square. Okay? So here we will have a quadratic equation, right? So we can either solve it like this, or we can substitute ID, or we can substitute VS, or we can substitute ID. एक तो ये ऐसे लिख सकते हैं, या दूसरा कैसे लिख सकते हैं, इसको we can write it as VS by RL equal to 1 milliamps per whole square into 4 minus VD of whole square. This is also another way of writing it. Both are equal, है ना?
Yes.
So you can solve either of the expressions. You will find ID or you will find VD. The moment you find VD, you will see that let's say the moment you find VS, you will see that since it is a quadratic equation, you will get two solutions, right? And if I am going by this VS method, I'll get two values of VS. One is 5.69 volts and other is 2.81 volts. Okay, and VD is fixed. VD is at 10 volts and VG is minus VTH should be greater than equal to VDS. If I say that SS are cancelled, then the VG minus VTH will always be equal or greater than VD. But if VS is 5.69 volts, what will be the value of VGS, which is 5 minus 5.69 volts? So VGS is actually less than 0. So यहाँ पे देखो, this condition always satisfies, which we always say कि this is the condition of saturation. But इस particular question में for 5.69, your actual condition, that is VGS should be greater than VTH, is the one which is failing. Correct?
Yes,
So
ma'am.
you remember once when we started MOSFET and we were talking about the conditions for saturation, I always said that you have to check the conditions. There are two conditions that you have to always check. One is VGS should be greater than VTH, and second is VGS minus VTH should be greater than VDS. Great. And most of the times, uh, as a habit, what we do, we only check VGS minus VTH to be greater than equal to VDS, and sometimes we forget to check like VGS to be greater than VTH, and that is where it causes the problem. As here you can clearly see, the moment we go for 5.69 volts as our RS, this condition fails immediately. And no matter whatever is your Vs, your transistor is in always saturation considering this condition 1. So what is the judging factor over here is actually the condition 2. So that is why it is very important to consider both the conditions. Okay. So so by this what we find out is this is the value of Vs that we will have, and it also makes sure that our transistor is in saturation. So since we have found out Vs and since we have found out Vs, we'll simply substitute this Vs over here and we'll find the value of Gm, right? So Gm will be 2 milliamps per volt square into Vg was 5 minus 2.81 minus 1 volt. So our GM actually turns out to be 2.4 millisiemens. Is this clear?
Yes, ma'am.
This discussion is clear? Okay.
Yes, ma'am.
With this discussion, let's move ahead. So the next problem is we have to find the voltage gain, that is V0 by Vn. What is the voltage gain for the
Ma'am, can you
amplifier?
hear me?
Sorry, yes,
Ma'am, actually there is one confusion.
Okay.
Well, I have some confusion.
Yes.
Ma'am, don't we have to ensure VDS should be get greater than VGS minus VTH?
We did, right? And what we actually found out is here we were finding Vs, okay? And it turns out this, if I spread it and write it, so it is like Vg minus Vs minus Vth greater than equal to Vd minus Vs. So if you see, if I add Vs on both sides, it will simply cancel.
No, ma'am. Actually,
Where?
maybe I am remembering wrong, but VDS should be greater than VGS minus VTH, right?
Oh, sorry. अच्छा ये साइन उल्टा हो गया है. अच्छा अच्छा अच्छा.
Yeah.
Okay. Yeah, ये साइन उल्टा हो गया. For saturation, VDS should be greater than. Yes. हाँ, साइन उल्टा हो गया. So my point of what I wanted to make a point is that actually when we are going for this condition, it becomes independent of Vs. So now how
Yes,
will you
correct.
judge like which Vs is correct? So that's where this first condition, which is VGS should be greater than VTH, comes into play. So that's what I wanted to make a point. But yeah, thank you. Yes, the sign was wrong, like it was inverted. So yeah. Now going for voltage gain. Yeah. So what is, how do we write voltage gain for MOSFET? Voltage gain is always GM into R naught, right? Or GM into Z out. GM we have already found out. What we have to find is Z out. So what will be the Z out for this particular circuit? Here. This is where we have to find Z out. So if I make, let's say I quickly make the small signal model for this. So from this point you will look for Z out, right? This will turn to ground. This will turn to ground. नहीं actually यहाँ पे तो green होगा. So yeah. So this is how the small signal model will look like, and this is our V naught or output point. So at this point we have to see Z naught. So if I say LC is Z naught, so it is actually RL parallel to R naught, which is parallel to 1 by GM. Be clear है? From the picture? See, when we are going for AC analysis, ये ground हो जाएगा. So the moment it is ground, मतलब your R naught, this terminal will be grounded. ये वाला GM वाला branch will be there, and this RL, and here it is the ground. So ground will always become a common ground. And when we see Z out from this node or this point, we'll see RL parallel R naught parallel 1 by GM. So R out will actually become 1 by GM plus 1 by R naught plus 1 by RL. So it is 1 by, how much was the GM? 2.4 milli, so 2.4 by 1000 plus R naught. How do we find R naught? What is R naught? So it is 1 by lambda IDS. Okay, 1 by lambda current, lambda into current for MOSFET. ठीक है? And RL is already given, so 1 by RL was 2K, so it's 2000 plus R naught. R naught में lambda we know, lambda was given to be 0.01 into ID. ID we have found Vs. So when we put this Vs over here, we'll find the value of ID, right? We have to simply substitute Vs. So Vgs minus Vth kW by 2L से we'll find ID, and that ID is actually IDS is I've calculated, wait, 1.405 milliamps. So when I substitute it here, 1.405, yeah. So this is the value for R naught, so which turns out to be 1 by 71K. So it is actually 71K. Okay. So from here R naught turns out to be 343 ohms. Now we have R naught, we have GM, so gain is GM into R naught, that is 2.4 milli into 343 ohms. So the gain actually turns out to be 0.82. What does this show? This is also less than 1. So the more it is closer to 1, it will act as a buffer circuit, and the lesser the gain than 1, it will act as an attenuator. Makes sense?
Yes, ma'am.
And what configuration is this circuit? This is CD amplifier.
Yes, ma'am.
This is drain, source, gate. So here drain is common. So this is CD amplifier. So similar to CC configuration in BJT, we have CD configuration in MOSFETs. Okay?
Yes, ma'am.
Yeah. So moving on. Here it is asked find the upper cutoff frequency of the gain of amplifier circuit shown. Upper cutoff frequency means you have to find the frequency. So if yeah, so we never talked about poles and zeros, right? Did we ever talk about poles and zeros? No, right? So when there is a AC signal coming, where let's say this is, I'll name the nodes A, B, C. Did I leave any node? No, right? D, E. Actually, E में ज़रूरत नहीं है. But yeah, so looking at these four nodes A, B, C, D, I am applying AC signal. So can you name all the nodes where you will see this AC signal coming into picture? Where all will you see the impact of AC coming into picture? There are four nodes, right? A, B, C, D. So out of these four nodes, where I'll see AC signals and where it is only DC? And how can you say? Are you getting my point? Hello? Hello? Am I audible?
Yes, ma'am, audible.
Yeah. So what I was asking is, like, if there are 4 points, okay, 4 terminals, we can say 4 terminals, 4 points, 4 nodes that we have. Out of these 4 nodes, which all nodes are AC nodes and which all nodes are completely DC nodes?
B node is going to be DC
Yes.
and D also.
B is going to be DC, yes. What about D?
D will have AC part.
Yeah, D will have AC, yes. What about C?
C will have both, I think.
Yeah, here also will have AC. DC भी है, तो AC DC कर देते हैं. What about A?
Both.
Yeah, actually both. AC and DC, right? So if we talk about MOSFET, like corresponding to MOSFET, so MOSFET, इस MOSFET पे ध्यान से देखो, इसका ड्रेन, गेट और सोर्स में, gate and source have AC signals, right? है ना? And when there are AC signals, it will have frequency response. And they will correspond to frequency response. And they will change with frequency. The behavior will change with frequency. So, the number of AC nodes, AC signal nodes, will actually maybe number of AC signal nodes equal to number of poles in the system. So you understand the pole zero system, right? There are poles, there are zeros. Signals and systems का जो poles and zeros होता है ना, pole is where your denominator goes to 0 and 0 is where your numerator goes to 0 in a transfer function. You understand that?
Yes.
Yes, ma'am.
Yeah. So your frequency response that appears, like which is gain versus frequency, so it's not always straight, but actually it's like it goes straight, then it comes down. And why it comes down? This is because of poles. So इसमें एक होता है गेन और दूसरा होता है बैंडविड्थ. Like when we are talking about amplifiers, there are few figure of merits which we need to keep in mind. As I was mentioning in very beginning of the classes, there are figure of merits as forms बोलते हैं, gain, bandwidth, then output swing, input swing, CMRR, and stuff like that. These are known as figure of merits for a given circuit. Okay. So gain, we all know, like how much your output increases for a given input. We all understand the concept of gain, right? Now when we talk about bandwidth, bandwidth means, let's say you have a gain of 50 dB. So till what frequencies your gain is like considerably 50 dBs. Okay. Or this point where it encounters a pole, it actually comes to 3 dB less, minus 3 dB frequency. You might have heard of minus 3 dB frequencies, right? We call them as cutoff frequencies also. Cutoff frequency नाम सुना है?
Yes, ma'am.
Yes, ma'am.
minus 3 dB frequency, cutoff frequency, low frequency, high frequency, ये सारी चीजें. So that actually defines the bandwidth of the circuit. That means कि कितना range of input frequencies के लिए your amplifier will behave as a linear amplifier, or it will give you the gain that you require. Right? The moment you reach, let's say you are giving this frequency f1, तुम्हारा gain has changed. It was earlier 50 dBs, but here it might be giving you 10 dBs. This is not what you want, right? और यहाँ पे it's continuously changing also. तो this is what is frequency response, and this is where the concept of cutoff frequencies come from. और जब हम बोलते हैं कि like there are AC signal nodes, these AC signal nodes actually introduce the pole in the system, and that pole actually defines this drop. Gain में जो ये drop है ना, it is defined by those poles. Okay. So let's say if in frequency I have two poles, 1 and 2. So the moment it encounters first pole, it will start dropping until it reaches the second pole. The slope will become even steeper. Have you heard of Bode plots?
Yes, ma'am.
Bode plots का नाम सुना है?
Yes, ma'am.
So what are Bode plots?
Ma'am, in that we have a graph of gain,
Yes, gain.
log, and frequency.
Yeah, gain versus frequency only, right? So that is also a frequency response. But it's a pictorial view, whereas frequency response means it is like actual view. So there also what we do, the moment we get a pole, we introduce a slope, right? Negative slope. So वही होता है real life में भी. The moment a system sees a pole, its gain starts dropping. So एक circuit का, it is very important to find out what are the poles. First of all, how many number of poles are there? Okay. After that, what are the values of those poles? And the smallest pole will have the largest impact. The smallest pole, see, when I have P1 and P2, the moment I encountered P1, P2 is of no use, right? क्योंकि यहाँ से जहाँ से drop होने लग रहा है मुझे वो point चाहिए ना. And this P1 will behave as my cutoff pole or cutoff frequency. Is this clear?
Yes, ma'am.
So we have to find, first of all, we have to find the number of poles in the system. Second, we have to find what is the smallest magnitude pole. Because the smallest magnitude pole is actually your cutoff frequency. Is this clear?
Yes, ma'am.
Okay. So with this discussion, let's move ahead. So I have told you, like, number of AC nodes will give you the number of poles in the system. So in this circuit that we are seeing, how many AC nodes are there? 2 AC nodes. Okay, which means 2 poles. And what is the value of those poles?
Ma'am,
Or
there are 3.
where are 3?
मैम ए डी है.
D को we can ignore for now, क्योंकि अभी मतलब ये जो S है ना, S is more important,
Yes, correct.
है ना, क्योंकि MOSFET के रेस्पेक्ट में अगर बात करें तो इट्स सिंपली अ लोड कैपेसिटर, राइट. सो वो S के करस्पॉन्डिंग ही हो जाएगा ना. आई कैन टेक C2 एंड CL एज अ कॉम्बिनेशन, राइट. क्योंकि why I'll come to that next. Why? Because poles or frequency, when we say, its value is actually 1 upon 2 pi RC. So जिस node पे you are considering, no, at that particular node you have to see the net capacitance coming to that node, or you can view from that node, and the net resistance you can view from that node. And then you'll simply substitute it in this formula, and you'll find the values of those frequencies or those poles, and the smallest pole will be your cutoff frequency or cutoff pole. Is this clear?
Yes.
So in this particular circuit, yes, there are 3 AC nodes, but here actually, if I talk about D node, there is no resistor involved, right? So it's not actually a node. If I say S, the source node, or C node, here I have resistance and capacitance, and I can combine C2 and CL together, right? I can simply combine C2 and CL together, and when it is AC, actually it will short your C2. So RL parallel CL will be your node, है ना?
Yes, ma'am.
When there is a AC signal, your C2 will be shorted. You will see RL parallel to CL. और similarly Cin के केस में भी, like input के केस में भी, this series capacitance will actually get shorted. So this will not come in picture. So you will see some other capacitances. Now what are those capacitances? So these are intrinsic capacitances to the MOSFET. Okay. So let's see what are the different capacitances that we have in a MOSFET. So when there is this MOSFET with gate, drain, gate, source, and there is another which is body, each and every terminal combined with one another, they have capacitances, okay, because they get coupled with one another. One terminal gets coupled with another. So this is known as CGS. This capacitor over here is known as CSB. This is known as CDB. So majorly we'll see these 4 types of capacitances. Okay. Most of the time source is shorted to body. Okay. To avoid the variation in to avoid any variation in VTH, threshold voltages, we always short source with body in the circuits. Okay, so that's why you will never see CSB. Why? Because C is dq by dV, right? Change in charge with change in voltage. But if 2 points are at same potential, there is no dV. तो C का तो कॉन्सेप्ट ही नहीं आता है ना. ये क्लियर है? Is this clear? Why CSB is 0?
Yes, ma'am.
Yes, sir.
Yeah. So with this, and secondly, let's say if 2 nodes are at DC, right? If D and G both are DC nodes and both are not changing, so again your dq by dV will be 0 for DC nodes. So then also that capacitor will not change. So you will not have any capacitance between those two nodes also. Okay? So only node which actually changes. So let's say for this particular case, your gate is having a DC value, whereas your source is a AC node. Your gate is a DC node, but your source is a AC node. Then this capacitor will actually look like this. It's connected from source to ground. Okay? Why? Because this is a DC node. That means it is DC shorted. Right? We talked about this, right? Capacitance कब आता है into picture? When we are going for AC analysis. And when we do AC analysis, we make small signal model. And in small signal model, what do? We put all the DC nodes to AC ground, right? So that same thing comes into picture here as well. Okay? And this becomes CGS, SGD, if this is a DC node. Clear?
Yes, ma'am.
समझ में है? Okay. So with that, now let's see what are the capacitance that we are actually going to see in this image or in this circuit. So here you see carefully, यहाँ एक capacitance होगा, right? This is GDS. This will be known as CGD. This will be known as CGS. And source or body is always shorted, so there won't be anything called source body, but there will be this capacitance called capacitance CDB. This that is drain and body, right? Because drain and body are at different potentials and it is connected to source. So here what happens is, when we are talking about input capacitance Cin looking from gate, here we will see that there is a capacitance which is between drain and gate and drain. This gate and drain will actually look like gate and ground, CGD, right? It will look like this in this circuit. Why? Because drain is AC grounded, है ना?
Yes, ma'am.
And there is this capacitance which is CGS. It is between two AC nodes. And whereas यहाँ पे अगर resistance की बात करें तो it will be R1 parallel R2, है ना? So this resistance that you are seeing over here, capacitance that you are seeing over here, which is between actually two nodes, two AC nodes, it is a problematic capacitor. Why? Because it is being shared between gate as well as source node, है ना? So I cannot write this capacitor completely as a part of gate, and I cannot even write it as complete part of your source. और यहाँ पे we will see another capacitor coming into picture जो कि होगा CDB, right? CDB आएगा ना? आएगा कि नहीं आएगा? आएगा, but this value is very small. CDB बहुत छोटा होता है, तो इसलिए in this yeah.
And that is source, ना?
हाँ, but source and body are shorted, right?
Source and body are shorted, but we are connecting CDB.
हाँ, CDB. So ये C अब ऐसा हो गया ना कि source and body एक ही terminal हो गया है because they are shorted. they have same potentials, everything is same, conditions are same for source and body. तो जो भी बॉडी से कनेक्ट हो रहा है वो अल्टीमेटली सोर्स से कनेक्ट हो रहा है, राइट?
But that should actually come from drain, right?
ड्रेन, बट ड्रेन इज AC ग्राउंडेड, राइट? इसीलिए तो ये देखो CGD में भी वो G से कनेक्ट हुआ, D से नहीं, बिकॉज ड्रेन इज अ DC नोड. DC नोड है ना, तो DC नोड से तो AC सिग्नल आएगा नहीं, तो वो AC ग्राउंड हो जाएगा ना, इसलिए वी आर मेकिंग द स्मॉल सिग्नल. क्लियर है? Okay, yeah. So what I was saying is this capacitor which is between gate and source is the problematic capacitor, and this is also known as Miller capacitor. Have you ever heard of this Miller capacitor?
Yes, ma'am.
You did, right? We have Miller capacitor, Miller effect. It is basically when anything is connected between input and output terminals, or when it is connected between two different two different terminals, we can say. When there is something which is connected between two different terminals and we cannot actually define it as completely part of one terminal, then that particular component is known as Miller's component. It can be Miller resistance, Miller capacitance, Miller impedance, it can be anything. So in our case it is actually a capacitor. So how does this Miller capacitor comes into play? So it is divided into two parts. One is input part, another is output part. It is divided such that in input your Cin will have CGS 1 minus AV, where AV is what? It's gain. Okay, तुम्हारे सर्किट का जो गेन है it depends on that. And when we talk about C out, it will actually come as a 1 minus 1 by AV, right? Plus minus. Or in short, if I want to write, I can write it as Cn as CGS times AV, and here it will become CGS. Yeah, it will simply become CGS because 1 by AV will be a very small number, right? So it will simply become minus CGS. है ना? So now there is something which is very interesting that you can observe. ये जो simple एक छोटा सा capacitor था CGS, when it is seen at output side, this is for input and this is for output. Okay. So when it is seen from input side, it actually becomes gain times of the capacitance. Whereas when it is seen from output side, it appears as that normal capacitance CGS. Right? So इसका मतलब अगर एक capacitor है which is very small but it is a Miller capacitor, then its impact on input size is gain times that capacitor. मान लो अगर gain 1000 का है, so your capacitance will increase by 1000 times, whereas output में it appears as is. So this is the issue that appears with Miller cap, and that's why you can see that we cannot neglect this Miller capacitor because it will become a very huge capacitance when it gets multiplied with the gain, right? ये समझ में आया? So that's why it is very important to analyze these Miller capacitances. So now, अब ये तो समझ में आ गया, हमें पता चल गया कि C in में actual capacitance कितना होगा और C out में कितना होगा, है ना? So if I'll add this CGS, I'll add it over here. Maybe I'll use some other color. I'll add our CGS over here as CGS 1 minus AV, and I'll add our CGS over here as CGS 1 by AV minus 1, है ना? So now we don't have to consider this. Now we have two different circuits, one for input, one for output, है ना? अब क्या करेंगे? हम simply इसको solve करेंगे. and here we will also have CL, and
Yeah.
yes.
Ma'am, is there any significance of minus or plus sign in reference to capacitance?
In reference to capacitance, no, not really, because
No.
we'll go for magnitudes. Like abhi bhi when we are talking about frequencies, we'll go for magnitude of R and magnitude of C. So it will be 1 by mod. But if I talk about in terms of stability, we can say that negative real frequencies are more stable. So it comes from our this picture, stability picture, where we have S plane, and we say like the negative side of your plane uh, gives you a stable circuit, whereas positive side of plane gives you unstable signals, unstable circuits. So it comes from that idea. So when we say negative frequencies, it is also regarding stability. Yeah.
Okay.
But in our terms, numerically, we'll go for magnitudes only.
Okay.
है ना? So अब हम लोग को क्या हो गया? We have two different circuits. We'll simply write 1 by 2 pi RC for input and output. And whatever is the minimum frequency, we'll report it as our cut-off frequency. इतना काम है. Clear? So let's write जल्दी से frequency for input. Input में 1 upon 2 pi. What is R? R is R1 parallel R2 for input. Input side, this is input. And this is output. So yeah, input में 1 by 2 pi R1 parallel R2 into C क्या है हमारा? CGS 1 minus AV into plus CGD. Plus क्यों? क्योंकि these are in parallel और capacitance में they get added. So ये जो frequency you will get, this frequency turns out to be 3.8 picofarads. Okay. And when we talk about frequency for output, here we will have 1 upon 2 pi RL into, what are the capacitors that are in parallel? CL plus CGS 1 by AV minus 1 plus CDB. But since the CDB is very small, so it's neglected. And also it was not mentioned, like its value was not mentioned in the question as well because of the same reason. So we will simply neglect. So it will be 2 pi RL. नहीं, RL भी नहीं. Here R naught will come because this intrinsic R naught was not 0, no, lambda was present. So it won't be RL, it will actually be R naught. Lambda 0 होने से वो direct RL हो जाता, but here we have a lambda factor, so it will simply become R naught, जो हमने last find out किया था, into CL plus CGS 1 by AV minus 1. Yeah. So when we put all the values and solve it, so the frequency that we'll get is 4.54 megahertz. And here the frequency, oh sorry, 1 second. इसमें input वाले में the frequency is 16.75 megahertz. This is for input, and for output we are getting 4.54 megahertz, and your cutoff frequency will be minimum of F in comma F out, so which is actually 4.54 megahertz coming from your input node. So this is your cutoff frequency. Yeah. Yes. So this is what we are getting. Now, how can we change our cutoff frequency if we want our output to be dominant, like our node to be dominant? We can simply increase the value of R naught, or we can simply increase the value of load capacitance. So our cutoff frequency will be output node dependent. So वो भी कर सकते हैं. And since load is something we apply externally, so we can change the value of loads. Because other things like even these R1, R2, all these circuits which we are using to, like all these components which we are using to design the circuit, they are internally made. ये IC के अंदर होता है. This complete part is inside IC. What you externally apply are load capacitances, load resistances, or any load that you apply are basically RC load. Most of them are RC load. जैसे fans वगैरह भी most of them are RC. Few are RLC also. Choke जैसे the tube light is RC load. Likewise, so most of them are RC loads. So you can change load, but you cannot change these internal bias circuits. So R1, R2, C1 तुम एक बार IC में design कर दिए, so it will be fixed like that. Now if you want to change your frequency, cutoff frequency, everything, so you can change depending on your load. So yeah, that is the thing. That is another idea that you get out of here. So ये समझ में आया? Is this clear? Okay, so we have headed over the time, but I hope today we have dealt with few things which were a little complicated and new stuff also, but I hope it is clear. If you have any doubt, feel free to contact, or we can discuss in next next session also. It's fine, but I hope it is clear. Do you have any doubts till now? Whatever we discussed about swings, frequency, cutoff frequencies and all. Any doubts? You can go through the lecture notes again. I'll upload it. You can also go through the video recording. I'll upload it also immediately. And so yeah, you can go through them. If you have subscribed, so it I guess the moment it gets uploaded, it shows you in the recommendation, right? The moment you subscribe to a channel. Yeah, so you can go through the this thing, video recording, and I'll upload the lecture notes also. Just in case if you have any doubts, you can ping me anytime. We can also talk about this in next week. So if no doubts, maybe we can end this session over here.
Oh, ma'am,
Yes.
you were saying you'll upload the notes. Ma'am, where can we find the notes?
Oh, so you people didn't get the link. So what? So we have been asked to share a link. So mine is a Google Drive's link. Google Drive's link where there is a folder. In that folder, I am uploading each and every week's notes. Like what I am preparing right now. No, I upload these notes as is. But you people don't have access to that link?
We have access to it now. Actually, it's on the NPTEL portal.
So NPTEL people might have shared that thing with you, but if you want, I can share that link with you. Do you want it right now? I can share it with you.
Ma'am, actually, if it is available on the portal, maybe I have missed out. I'll check on the portal so that you don't have to upload again and again.
Okay.
I'll
Yeah,
just
because
check on the portal.
yeah, because every time I upload my notes over there, so you people have never gone through the notes. So if there is,
I was just looking for the notes, but maybe I didn't reach the right point where it was uploaded. So it is my fault, maybe.
or
That's why
maybe if you
for it.
want, it's not a big deal. I'll simply share my drive link here itself, so you can go.
Yeah,
through.
but if it's very simple, then you can just do it. It will be easier as well.
Yeah, maybe I'll stop the recording and I'll share the link with you. Wait for a minute. You two can at least access. Yeah.
Okay.